Neptune has been cooling for 17 years during summer. At the same time, its south pole heated up by 20 degrees Fahrenheit in 24 months. And in between those two events, every single cloud on the planet vanished completely. Not reduced, not thinned, gone. A blue sphere that had worn bright white cloud bands through every decade of modern observation was suddenly bare. Scientists had no framework for any of it. Not individually, and certainly not all three happening simultaneously. That is where this story begins. Not with a mystery invented to hook your attention, but with a genuine scientific breakdown. A planet. The models said they understood doing things the models said it could not do. Neptune sits 2.8 billion miles from Earth. That distance is so large that light, traveling at 186,000 miles per second, takes more than 4 hours to cross it. The same light reaches Earth in 8 minutes. This is not just a matter of degree. 2.8 billion miles puts Neptune in a fundamentally different category of far. It is far in a way that changes how science can be done there, how long observation campaigns must run, and how much a scientist has to accept about what they will never personally see confirmed. For most of human history, nobody knew Neptune existed. You could spend a lifetime staring at the night sky, memorizing every star, tracking every visible planet, and Neptune would never reveal itself. Mercury, Venus, Mars, Jupiter, Saturn, all of them visible to the naked eye. Ancient astronomers catalogued them, tracked their movements, built religions around them. Neptune waited in the dark, too dim, too distant, invisible, without tools that would not exist for centuries. Even after telescopes arrived and brought the heavens into sharper focus, Neptune stayed hidden. Astronomers were cataloguing what was already in front of them. Nobody went looking for what they did not know to look for. The discovery, when it finally came in 1846, did not come from anyone looking through a telescope at the right patch of sky. It came from a mathematician sitting with equations. Astronomers in the early 19th century were proud of their celestial mechanics. The mathematics that governs how planets move was considered essentially complete. They could calculate where any known planet would be in the sky on any given night with impressive precision. Uranus, discovered in 1781, was one of those known planets, and for a while its position tracked the predictions perfectly. Then it stopped. Small deviations at first, barely noticeable. But over years and then decades, the gap between where Uranus should have been and where it actually was kept widening. Something was pulling it sideways, something massive, something unseen, something with enough gravitational force to tug an ice giant off course every time the two worlds swung within range of each other. Two mathematicians, working independently and without any knowledge of each other, arrived at the same conclusion. There had to be another planet out there beyond Uranus. They used only math to find it. No telescope, no image, just equations describing orbital mechanics and gravity. They each drew a spot on a map of the sky and said to look there. An astronomer in Berlin pointed a telescope at that spot in September of 1846. Neptune was sitting exactly where the equations predicted. That is one of the greatest predictions in the history of science. These mathematicians had never seen Neptune. They had no physical description of it, no photograph, no way to confirm it existed before the telescope confirmed it in a single night. They trusted gravity completely, and gravity delivered. But there is a wrinkle in the story that rarely gets told. The astronomer who made the discovery could find Neptune so quickly because he had access to a detailed star chart of that precise region of sky, created just months earlier by another astronomer who had mapped that region without knowing a planet was hiding there. Neptune had appeared on that chart. It was recorded as a background star. Nobody was looking for a moving object, so nobody noticed it. Neptune sat on paper for months before anyone identified it as a planet. That detail says something specific about this world. Neptune has a habit of sitting directly in front of you while remaining completely mysterious. A century and 43 years after its discovery, humans got their first real close look. NASA's Voyager, 2 spacecraft had been traveling across the solar system for 12 years when it reached Neptune in August of 1989. What it sent back was startling. A vivid, deep blue planet wrapped in bright cloud bands. An enormous, dark, oval storm system spinning in the southern hemisphere, roughly the size of the entire Earth. Companion methane ice clouds swirling along its edges, and wind speeds that broke every record in the solar system. Scientists had expected a cold, quiet, frozen world. Neptune looked alive. It looked violent. It was nothing like what the distance alone had suggested it would be. Voyager 2 did not slow down. It passed through and continued on its path out of the solar system, never to return. Scientists got a snapshot, not a film. Everything learned since then has come from telescopes on the ground and in orbit, staring across 2.8 billion miles of space. Trying to read the faint signals a nearly invisible planet sends back in wavelengths of light the human eye cannot see. And in 2003, some of those telescopes began detecting something nobody expected. To appreciate what the data was showing, you need to understand Neptune's seasons. Like Earth, Neptune has a tilted axis. It leans about 28 degrees relative to its orbit. Earth leans at roughly 23.5 degrees. And that tilt is why our planet has seasons. When your hemisphere tilts toward the sun, sunlight arrives more directly. Temperatures rise. Summer comes. Neptune works by the same physical principle. As it crawls through its orbit, different parts of the planet tilt toward or away from the sun. The difference is the time scale. One Neptune year lasts 165 Earth years. One season lasts about 40 Earth years. 40 years. A child born at the start of a Neptune summer would be middle-aged before summer ended. A scientist who dedicated their entire professional career to watching a single Neptune season from start to finish would only see one cycle, one pass through one chapter of the planet's year, with no second opportunity to confirm whether what they observed was typical or bizarre. Neptune entered its southern hemisphere summer around 2005. The South Pole began its long, slow tilt toward the sun. Scientists had been watching with thermal infrared cameras since 2003, setting up a baseline before summer officially arrived. Thermal infrared cameras detect heat the human eye cannot see. Pointed at a planet across billions of miles, they measure how much energy the atmosphere is radiating at different latitudes and altitudes, which scientists convert into temperature values. Building that temperature record required years of telescope time at some of the most oversubscribed observatories on Earth. The expectation was clear. South Pole summer means more sunlight hitting the southern hemisphere than at any point in the previous 40 years. More sunlight means more absorbed energy. More energy means rising temperatures. The models built on decades of planetary science, orbital mechanics, and atmospheric physics all pointed the same direction. A slow, steady, predictable warming curve at the South Pole as summer progressed. The data told a completely different story. When scientists assembled the full thermal record from 2003 through 2018 and traced the temperature curve, the line went down. Not at the South Pole specifically, not in one region, across the entire planet. The global stratosphere had dropped 14 degrees Fahrenheit during the first 15 years of summer, 14 degrees globally, during summer. To put that in human terms, consider Earth's climate. The difference between a full ice age and the warm interglacial period we currently live in is roughly 9 degrees Fahrenheit averaged across the whole planet. That 9-degree difference buried continents under ice sheets kilometers thick. Neptune's stratosphere lost 14 degrees in 15 years during a season when every model available predicted it should have been warming. Scientists ran every check they could think of. They revisited their calculations. They cross-referenced data from multiple telescopes at multiple observation sites to make sure no single broken instrument was feeding false readings into the results. The signal was consistent everywhere they looked. The cooling was real. Something inside Neptune's atmosphere was actively removing heat from the stratosphere, either trapping it somewhere else in the system or venting it directly into space through mechanisms nobody had modeled. The stratosphere is the layer of atmosphere sitting above the active weather zone. On Earth, it is the calm, high region where commercial aircraft cruise above the clouds and storm systems. Neptune's stratosphere sits in a similar position relative to its weather layer. It plays a key role in regulating the planet's overall energy balance. When it cools by 14 degrees globally over 15 years, the signal is unambiguous. An enormous amount of energy is leaving that part of the system faster than it is arriving. Scientists ran through the possible mechanisms. The Sun was the first candidate. If solar output dropped, Neptune would receive less energy and might cool. But the Sun's 11-year activity cycle does not produce sustained drops large enough to drive a 15-year cooling trend of this scale. Solar variability was real but insufficient on its own. The next candidate was Neptune's own atmospheric chemistry. The upper atmosphere contains gases including methane and hydrogen cyanide, along with other compounds that absorb and emit heat at specific wavelengths. If the balance of those chemicals shifted, the stratosphere might have become more effective at radiating energy outward into space rather than trapping it. This process is called increased radiative cooling, the atmosphere becoming better at venting heat. But scientists could not confirm which chemical change triggered the shift or what triggered the chemical change in the first place. Then there was internal variability, the chaotic behavior that complex atmospheric systems generate on their own, independent of any external forcing. Neptune's atmosphere might simply cycle through extreme temperature fluctuations as part of its normal behavior, and humans had never watched long enough to catch this before. The problem with that explanation is the scale. A 14-degree global shift in 15 years is not minor atmospheric noise. It requires a powerful and sustained mechanism, especially one capable of working against the additional solar energy arriving at the South Pole as summer began. Scientists had real data, a strong signal and no confirmed mechanism. That situation was already scientifically extraordinary. Then Neptune added another data set that made the cooling look almost calm by comparison. In just 2 years, between 2018 and 2020, the temperature at Neptune's South Pole stratosphere shot upward by 20 degrees Fahrenheit. A single region on a planet that was globally losing heat suddenly and rapidly overheated. 20 degrees in 24 months. In human everyday terms, 20 degrees is the difference between a comfortable autumn day and a cold snap that sends people reaching for coats. It is the difference between liquid water and ice. On a planetary scale at stratospheric altitudes, gaining 20 degrees in 2 years is extraordinary. Scientists had no recorded precedent for this kind of rapid, localized polar warming on any outer planet in the solar system. The warming was tightly confined to the South Pole region. It did not spread gradually across surrounding latitudes. It spiked in one specific area while the rest of the planet remained deep in its 15-year cooling trend. This created a sharp temperature boundary, a zone where extreme heat at the pole met extreme cold everywhere else, separated only by latitude, not by any wall or physical barrier, just by the atmosphere itself. A temperature contrast like that drives atmospheric circulation. Hot air rises, cold air sinks. Where they meet along a sharp boundary, powerful wind systems develop. On Neptune, where sustained winds already reach 1,200 miles per hour under normal conditions, a temperature boundary this extreme would generate atmospheric dynamics that exceed anything in the planetary science catalogue. Scientists proposed several possible explanations for the polar spike. One involved solar energy accumulation. As the South Pole spent increasing time tilted toward the Sun through the opening decades of summer, solar radiation may have been slowly building up in the polar atmosphere in ways that were not immediately visible in the temperature record, like pressure building in a sealed container. Then, at some threshold, that stored energy may have released rapidly, driving the sudden spike. But this explanation requires a mechanism for storing and then suddenly venting atmospheric energy at a very specific location, and no such mechanism has been confirmed. Another possibility involves atmospheric chemistry. A shift in the concentration of certain gases at the South Pole might have altered how efficiently the polar stratosphere trapped heat. But again, the specific chemistry is not confirmed. The temperature record is real and precise. The cause remains open. What makes the polar spike particularly significant is its timing. The South Pole registered its sharpest warming between 2018 and 2020, the same period when the global stratospheric cooling reached its minimum. The coldest point on the planet overall and the hottest point at the pole coincided almost exactly. Either these events are connected and one is driving the other through some mechanism that transfers heat from the global atmosphere into the polar region, or they are independent and Neptune's atmosphere is capable of generating simultaneous extreme events in opposite directions at the same time. Both possibilities are uncomfortable for the same reason. Neither was predicted. Neither appears in any planetary model. And while scientists were working to reconcile these two temperature extremes, the planet presented a third data set, one that was visible in photographs. For 3 decades of modern observation, Neptune had been recognizable by its bright white cloud bands. Every major telescope image from the late 1980s onward showed them. Long, wispy streaks at high altitudes, compact bright knots at lower levels, active weather features that made the planet look alive and dynamic against its deep blue background. When Voyager 2 flew past in 1989, it captured those clouds in stunning detail. When Hubble began regular monitoring in 1994, it documented them year after year. Neptune's clouds are not water clouds like Earth's. They form from methane ice crystals. Neptune's upper atmosphere contains methane gas. At high altitudes where temperatures drop far below freezing, some of that methane freezes into tiny solid ice crystals that cluster into visible cloud formations. These methane ice clouds sit high enough to catch sunlight and reflect it brightly against the planet's blue background. The deep blue color itself also comes from methane, but from methane gas lower in the atmosphere, where it absorbs the red portion of incoming sunlight and reflects the blue wavelengths back outward. The entire visible face of Neptune is a methane story told in 2 different physical states of the same molecule. Through the 1990s and 2000s and into the 2010s, those clouds were always there. Some years showed more activity, some less. There was year-to-year variation. But the basic presence of bright cloud features remained consistent through every observational period. They were part of the expected picture of Neptune. Students learning the planet saw those cloud bands. Scientists built models that included them as a standard feature of Neptunian weather. The disappearance was not noticed in real time. That is one of the most important details in this whole story. It was discovered the same way you might notice that a gradual change in your own habits had quietly transformed into a new pattern, only after stepping back far enough to see the full arc. A research team collected and analyzed every usable telescopic image of Neptune taken between 1994 and 2020. 26 years of photographs from Hubble and from ground-based observatories. Each image captured Neptune's cloud brightness, a measurable quantity reflecting how much reflective material was present in the atmosphere at that time. When researchers plotted those brightness values across all 26 years, a pattern emerged that no one had clearly seen before. The brightness values fluctuated year to year as expected, but underneath those short-term variations, a long-term decline was running. A slow drift downward in average cloud brightness that accelerated sharply after 2015 and reached near zero around 2019 and 2020, seeing the full 26-year record made it undeniable. Each individual observer watching Neptune in any given year had seen a quiet year rather than a catastrophe. The gradual nature of the decline playing out over more than a decade kept it invisible to anyone looking at short windows of data. The signal only became clear when someone stepped back far enough to see the complete shape. And what the complete shape showed was a planet that had been systematically losing its clouds across an entire human generation of observation. By 2020, Hubble photographs showed a Neptune that was visually transformed, a smooth, uniform blue sphere. No white streaks, no bright cloud knots, no visible atmospheric texture of any kind. Just blue, the transformation from the cloud-streaked Neptune of the 1990s to the bare blue marble of 2020 was striking enough that scientists who had studied the planet for decades described the images as looking stripped. Something had been removed. That description was literally accurate. The disappearance carries specific scientific meaning beyond its visual strangeness. Clouds are not passive decorations. They actively participate in atmospheric circulation. They reflect sunlight back into space, affecting how much solar energy the planet absorbs. They release heat when they form and absorb heat when they evaporate. They mark the locations of updrafts and storm systems. When the clouds vanish, scientists lose one of their primary tools for tracking what the atmosphere is doing. A featureless Neptune is instrumentally quieter as well as visually quieter. The markers that helped scientists read the planet's dynamics had been removed along with the clouds themselves. Scientists noticed something about the timing. The cloud disappearance bottomed out around 2019 and 2020. Those years coincided with a solar minimum, the quietest point in the Sun's 11-year activity cycle. That observation opened a new line of investigation. The Sun operates on an 11-year cycle. At solar maximum, the Sun erupts with flares, launches charged particles throughout the solar system, and floods surrounding space with intense ultraviolet radiation. At solar minimum, it is quieter, producing less of everything. This cycle shapes conditions across the entire solar system. On Earth, solar maximum can disrupt satellite communications and power grids. Auroras burn brighter. The upper atmosphere expands measurably. These effects are real even from our relatively close distance. Neptune sits 2.8 billion miles away. At that distance, the Sun looks like a bright star. The total amount of sunlight reaching Neptune is roughly 900 times weaker than what reaches Earth. Scientists assumed the enormous distance would dilute the Sun's 11-year cycle to near irrelevance for Neptune's atmosphere. That assumption was wrong. When researchers overlaid the solar activity record against Neptune's cloud brightness data from the 26-year photographic archive, a pattern appeared. Neptune's clouds were more abundant during periods of high solar activity and less abundant during quiet periods. The correlation was not perfect, but it was consistent enough to be statistically meaningful across multiple solar cycles within the observation window. There was also a lag. Solar activity would peak, and then roughly 2 years later, Neptune's clouds would reach their highest abundance. 2 years of delay across 2.8 billion miles of space. The lag makes physical sense. Ultraviolet radiation from the Sun does not instantly rearrange atmospheric chemistry on a distant planet. It triggers slow chemical reactions that build gradually over months and years before producing a visible result. The mechanism works like this. Ultraviolet radiation from the Sun, the same kind that causes sunburn on Earth and gets blocked by sunscreen, travels 2.8 billion miles across space and reaches Neptune's upper atmosphere. There it collides with methane molecules at high altitude and breaks them apart. The fragments react with nearby nitrogen and hydrogen molecules, producing more complex chemical compounds. One group of products of this process is a family of haze-forming particles called tholins, reddish-brown organic compounds that form in cold atmospheres exposed to radiation. These particles drift downward through the atmosphere as tiny, solid specks. At a certain altitude, temperatures drop cold enough for methane gas to freeze onto the surfaces of these particles. The methane ice coats them and builds up until you have clusters of small, bright ice crystals. Those clusters are Neptune's clouds. The particles serve as seeds around which ice crystals nucleate. Without the seeds, methane ice has no surface to grow on. When solar activity is high and ultraviolet radiation is intense, the cloud factory runs at full capacity. More seeds form in the upper atmosphere. More seeds mean more nucleation sites for methane ice. More crystals mean more clouds. When solar activity drops and ultraviolet intensity falls, fewer seeds form. The supply of nucleation sites thins. Methane ice cannot form efficiently. Existing clouds disperse. The atmosphere clears. This is called photochemical cloud seeding, and it explains why Neptune's cloud abundance tracks the solar cycle with roughly a 2-year lag. The lag comes from the time required for ultraviolet radiation to drive photochemical reactions, produce the seed particles, let them drift to cloud-forming altitude, and allow methane ice to build up on their surfaces. The discovery that this mechanism operates across 2.8 billion miles, responding to the Sun's 11-year rhythm on a planet that receives 900 times less solar energy than Earth, was genuinely unexpected. It also immediately raised a deeper question. If the solar cycle can control Neptune's cloud factory through this photochemical pathway, what else might it be influencing? The same ultraviolet-driven reactions that produce cloud seeds also produce other compounds that absorb or emit heat at specific wavelengths. If solar activity changes the concentration of those heat-active compounds, it might also alter how efficiently Neptune's stratosphere radiates energy into space. That connection between the solar cycle and the deeper stratospheric cooling is one of the pieces the models most urgently need, and it remains unconfirmed. What scientists can say with confidence is that 3 simultaneous and dramatic atmospheric events all unfolded on Neptune across roughly the same decade. The global stratosphere cooled 14 degrees over 15 years. The South Pole spiked 20 degrees in 2 years. Every cloud on the planet disappeared. 3 events, each more extreme than any model predicted, each happening at the same time. Either they share a single underlying cause, or Neptune's atmosphere is capable of generating multiple simultaneous failures of existing models at once. Neither conclusion is reassuring if your job is building accurate models of planetary atmospheres. The temperature record that revealed all of this was built from 95 thermal infrared images collected across about 20 years of coordinated observation. 95 images. Over 2 decades, spread across multiple observatories on 2 continents and 1 space-based instrument. That number sounds modest until you understand what producing each one required. The Very Large Telescope sits in Chile's Atacama Desert, perched on a mountain at about 8,500 feet of elevation. The Atacama is one of the driest places on Earth. On most nights, the air above it contains almost no water vapor. Water vapor absorbs infrared radiation, making dry air essential for thermal infrared astronomy. The telescope consists of 4 separate mirrors, each about 27 feet across, that can operate together as a combined instrument. When working in combined mode, the system achieves resolution that would require a single mirror roughly 130 feet wide to match, on the other side of the Pacific, on the summit of Mauna Kea in Hawaii at nearly 14,000 feet of elevation. 2 other major observatories contributed to the Neptune record. The Keck Observatory houses 2 telescopes each with a mirror about 33 feet across. The Subaru Telescope, operated by Japan's National Astronomical Observatory, uses a single mirror about 27 feet across and carries instruments specifically designed for near-infrared and thermal imaging. Mauna Kea's elevation places it above a significant portion of Earth's water vapor layer. Conditions on the summit are bitterly cold with winds that can shut down operations entirely. The people who run those observatories work in genuinely harsh conditions to produce data of this quality. The combination of Chilean and Hawaiian sites gave the monitoring program geographic redundancy. When weather blocked observations from one location, the other might provide a clear window. Over 2 decades, the 2 locations together delivered the 95 images that built the temperature record. Processing each image required correcting for Earth's own atmospheric interference, aligning images taken years apart by different instruments, and calibrating the temperature scale consistently across the entire dataset. Each image went through an extensive reduction pipeline before a usable temperature measurement could be extracted. Scientists are not reading Neptune's temperature as a single exact number. They read it as a range, for example, minus 340 degrees Fahrenheit plus or minus 4 degrees. Across 95 images, individual uncertainties average out. The trend signal, the consistent long-term direction of temperature change, emerges more clearly as data points accumulate. A single unusually cold reading could be instrument error. A 15-year trend confirmed across multiple instruments at multiple sites is real. The ground-based observatories also received support from space. NASA's Spitzer Space Telescope, which launched in 2003, spent over 16 years conducting infrared astronomy from orbit. Its detectors were chilled to temperatures near absolute zero using liquid helium, making them sensitive to infrared signals too faint for ground-based detection. For Neptune, Spitzer provided clean baseline measurements uncontaminated by Earth's own atmosphere, helping calibrate and validate the temperature values derived from the ground telescopes. When Spitzer detected a temperature value in a wavelength range that ground telescopes could also measure, and the two matched, confidence in the measurement increased. Where they diverged, scientists knew to look more carefully at potential sources of error. Spitzer ran out of liquid helium coolant in 2009, which ended its most sensitive operations, but it continued contributing to the Neptune record until NASA retired it in 2020. The deeper lesson from this monitoring infrastructure is about how science actually works on questions like these. No single telescope, however powerful, can answer a complex question about a distant planet alone. The Neptune temperature record required a network, multiple ground-based observatories on 2 continents, a space telescope above the atmosphere, and a coordinating team managing the combined data stream across decades. The teams running this campaign competed for telescope time at oversubscribed observatories year after year. Each allocation of time to Neptune came at the cost of some other project that did not get scheduled. Sustaining that commitment across 20 years required institutional patience that is genuinely rare in science. The data it produced revealed a planet whose atmosphere was doing things no model had anticipated, and understanding why required tools of a completely different order. The James Webb Space Telescope launched in December of 2021. After a 6-month deployment and calibration process, it began science observations in mid-2022. Within its first year of operation, it turned toward Neptune. Webb's primary mirror is about 21 feet across, nearly 3 times wider than Hubble's, but size is not the primary difference for Neptune science. Webb is optimized for infrared wavelengths, the same part of the light spectrum that carries heat information from planetary atmospheres. Its detectors can resolve wavelength features in infrared spectra with a precision that allows scientists to identify specific molecules in an atmosphere and measure their concentrations. This is the chemical fingerprint that scientists needed to investigate the mechanisms behind Neptune's temperature changes. The first Webb images of Neptune, released publicly in late 2022, showed something Hubble had never captured with this clarity. The planet's faint ring system was visible alongside the planet itself, and the polar region came through with a sharpness no previous instrument had achieved. But the science value runs deeper than the images. Webb's spectroscopic instruments can analyze the composition of Neptune's upper atmosphere by measuring which infrared wavelengths the atmosphere absorbs and emits. Different molecules absorb at different wavelengths. By mapping the absorption pattern, scientists can identify which gases are present and roughly how abundant they are. If methane concentrations change between 2003 and 2020 in ways that altered the stratosphere's ability to retain or release heat, Webb can detect current methane levels and compare them to historical estimates. If other gases such as hydrogen cyanide or ethane shifted in concentration, those shifts would appear in Webb spectra. The warm polar stratosphere created by the 20-degree spike left a particular chemical signature to look for. A warmer polar region would change the vertical distribution of gas species. Gases that condense at lower temperatures might remain as vapor at higher altitudes. Photochemical products might accumulate differently in a warmer zone. Webb's sensitivity is sufficient to detect compositional differences between the polar region and the surrounding atmosphere. Scientists also expect Webb observations over the coming years to track how Neptune's atmosphere evolves as it moves deeper into southern hemisphere summer. The South Pole is still in summer. It will remain in summer for roughly another 2 to 3 decades. Whether the polar spike was a one-time event or the beginning of a longer warming trend is a question that sustained monitoring can eventually answer. Webb's operational lifetime is estimated at roughly 20 years based on fuel reserves. For Neptune science, 20 years of Webb observations would cover roughly half of one Neptune season, a far more meaningful fraction of the full seasonal cycle than previous instruments ever achieved. The complete picture may take decades, but the tools to find it are now running. Before those tools can deliver the answers, it helps to understand what is happening inside Neptune itself. Because the interior is as strange as the atmosphere, Neptune receives almost no energy from the Sun. At 2.8 billion miles, the sunlight arriving at Neptune carries roughly 900 times less energy per square foot than the sunlight hitting Earth. Scientists long assumed that a planet this remote would be almost entirely dependent on that faint solar input to maintain whatever thermal state it had. Neptune corrected that assumption completely. Measurements of Neptune's energy budget reveal that the planet radiates more than twice as much heat into space as it receives from the Sun. The difference is enormous. Neptune is not simply reflecting solar energy back outward. It is generating its own internal heat at a rate that dwarfs its solar income and pumping it into space continuously. This internal heat source has been known since Voyager 2's flyby confirmed it in 1989. Its precise origin remains one of the deeper questions in Neptune science. The leading explanation is that Neptune is still slowly radiating heat left over from its formation roughly 4.5 billion years ago. Planet formation involves enormous collisions between rocky and icy bodies accumulating under gravity, releasing tremendous heat. A planet as massive as Neptune takes billions of years to radiate that primordial energy away completely, but the math does not close cleanly. The rate at which Neptune sheds internal heat suggests either that its formation was unusually energetic or that an additional ongoing process is generating heat in the interior, right? Now, one candidate is the slow settling of denser materials toward the planet's core, a process called differentiation. As heavy materials sink inward through Neptune's interior over geological timescales, they release gravitational energy as heat. This process is ongoing and provides a steady internal heat source. The internal heat output matters for understanding the temperature changes observed at the surface because internal heat drives convection in the lower atmosphere, and convection shapes the thermal structure of the layers above it. If something changed in how Neptune's internal heat moved through its lower atmosphere and into the stratosphere between 2003 and 2020, it could have influenced the stratospheric temperatures scientists were measuring. Nobody has confirmed whether internal heat transport changed during the observation period. The lower atmosphere is far harder to measure than the stratosphere. The instruments that built the temperature record were sensitive to stratospheric altitudes, but had limited visibility into the deeper weather layer where internal heat enters the atmospheric system. The stratosphere is the visible tip of a far deeper and more complex thermal engine. The temperature changes documented at the top may reflect processes happening far below that existing tools were never designed to see, and those processes deep inside Neptune where no instrument has ever reached and none will for the foreseeable future. include phenomena that seem to belong more in a science fiction scenario than in a planetary science textbook. Deep inside Neptune, it rains diamonds. This is not a metaphor, and it is not speculation. Experimental physics and computational models both support it. Under the extreme pressures and temperatures found deep within Neptune's interior, carbon atoms get squeezed together so tightly that they bond into diamond crystal structures, forming solid gems that fall through the liquid interior like precipitation falling through air. To understand how this happens requires understanding the conditions at depth. Neptune's interior is not a simple ball of gas. As you descend through its atmosphere, pressure builds with increasing force at every deeper level. By the time you reach the region scientists call the mantle of Neptune, you are under pressures millions of times greater than the pressure at Earth's sea level. Under those conditions, methane molecules that make up part of the interior composition get broken apart by heat and pressure. The carbon atoms released cannot exist in their normal form at those pressures. They get forced into the rigid crystalline lattice of diamond. Groups of these carbon atoms bond together, forming small diamond crystals. Diamonds are denser than the surrounding fluid material, so they sink. They fall inward toward Neptune's core. Scientists confirmed this process not by reaching Neptune's interior, but by recreating the conditions in a laboratory. Researchers fired intense laser pulses at a plastic material that mimics the hydrocarbon-rich interior composition of Neptune. The lasers compressed and heated the target so rapidly that for a fraction of a second, the conditions inside the chamber matched those deep inside a distant ice giant. Instruments detected the formation of diamond-structured carbon within that brief experimental window. The experimental confirmation has come from multiple institutions and has been replicated. Diamond rain in ice giant interiors is now one of the more confidently supported exotic phenomena in planetary science. The diamonds forming inside Neptune right now are not gemstones you could hold in your hand. They likely form as tiny crystals or clusters of crystals, though some models suggest they could grow larger over time as they fall through the interior. A proposed scenario involves diamonds eventually reaching a region near the core where conditions change, causing them to dissolve back into the surrounding material or pool at the core boundary. Some researchers have speculated that this accumulation of dense material near the core might contribute to Neptune's internal heat generation. As settling releases gravitational energy, that connection between diamond rain and the heat. Budget of Neptune's atmosphere is speculative. The interior is entirely inaccessible to direct observation. No instrument has ever entered Neptune's atmosphere, let alone approached its deep interior. But the physics is solid. Under those pressures, carbon behaves that way. The diamonds are forming and falling inside Neptune right now, even as scientists on Earth are still working to understand why its clouds disappeared. Neptune's winds are equally extreme. At the cloud tops, sustained wind speeds reach 1,200 miles per hour. A commercial aircraft cruises at roughly 550 miles per hour. Neptune's winds move more than twice that fast. 1,200 miles per hour is the fastest sustained large-scale wind speed recorded on any planet in the solar system. Not the fastest gust inside a localized storm, but the characteristic speed of the planet's general atmospheric circulation. What makes these winds even stranger is their direction. Neptune spins from west to east, the same rotation direction as Earth, but the main wind patterns in its atmosphere flow from east to west, against the spin direction. This retrograde wind pattern is something scientists still find difficult to explain. The energy source for winds on a planet this far from the Sun cannot be sunlight, which arrives 900 times weaker than at Earth. The energy driving 1,200 mile-per-hour winds across a planet, the volume of nearly 60 Earths, comes predominantly from Neptune's internal heat. Heat rising through the interior drives convection in the lower atmosphere. Neptune's rapid rotation, which completes in just about 16 hours, organizes that convection through the Coriolis effect into large-scale wind patterns. But why those patterns flow against the planet's spin at speeds unmatched anywhere in the solar system, remains an open question in planetary fluid dynamics. The winds shaped what scientists observed in the cloud record. During years when Neptune had active cloud cover, those clouds moved visibly across the planet's disk between successive telescope observations. The rate of that movement gave scientists a way to measure wind speeds indirectly from images taken across billions of miles of space. Some of those cloud-tracking wind measurements helped confirm the 1,200 mile/hour figure. When the clouds disappeared, scientists lost that wind-tracking tool. A cloudless Neptune was not just visually featureless, it was instrumentally quieter, stripped of the atmospheric markers that helped scientists read the planet's dynamics. Neptune also has rings. This surprises many people, who associate rings primarily with Saturn's brilliant wide bands. Neptune's rings are different. Discovered in 1984 through stellar occultation, a technique that involves watching a distant star and measuring what happens to its light as a planet passes between the star and Earth, they were found to be incomplete. The starlight dips before and after the planet's passage were asymmetric. The rings appeared to block starlight on one side of the planet, but not the other. Instead of continuous bands all the way around, Neptune has arcs, partial rings covering only portions of their orbital paths. Voyager 2 confirmed the arcs in 1989, photographing 5 main rings surrounding Neptune. All are faint and dark compared to Saturn's brilliant ice rings. 3 of the 5 contain denser clumps of material forming the arcs, while the rest of the ring between those clumps is thin and nearly invisible. These arcs have a stability problem. Orbital mechanics predicts that material in a ring should spread out over time as particles at slightly different speeds gradually diffuse, distributing the clumped material uniformly around the full ring. Standard calculations say an arc should smooth itself into a uniform ring within a few thousand years. Neptune's arcs have persisted for at least decades, and possibly much longer. Something is keeping the material clumped. The leading explanation involves gravitational resonance with one of Neptune's small inner moons. A moon orbiting at precisely the right distance creates a gravitational rhythm that confines ring particles into specific zones, acting as a fence preventing the material from spreading freely. Neptune's moon Galatea, orbiting just inside the main ring arc region, is the primary candidate for this shepherding role. The ring arcs are made of dark material, likely a mixture of ice particles coated with carbon-rich compounds darkened by billions of years of radiation exposure. Their dark color is why they are so much harder to see than Saturn's bright ice rings. They absorb light rather than reflecting it. More recent observations with Hubble and ground-based telescopes have tracked changes in the arcs over the decades following Voyager 2's flyby. Some portions have brightened or dimmed. The arcs appear to be slowly evolving, possibly due to collisions between ring particles, ongoing gravitational shepherding dynamics, or material exchange with nearby moons. The rings are another reminder that Neptune carries complexity at every scale. From the deep interior, where diamond crystals fall through liquid layers, through the turbulent weather layer where storms vanish and clouds disappear, out to the faint arcs of dark debris orbiting silently in the cold beyond. Neptune's color is itself a chemical record. The deep, rich, saturated blue that makes it one of the most visually striking objects in the solar system comes entirely from methane. Methane in Neptune's atmosphere absorbs the red wavelengths of incoming sunlight preferentially. Red light gets captured by methane molecules and converted to heat. Blue and violet wavelengths pass through methane with minimal absorption and reflect back outward. The result is that the light bouncing back from Neptune toward a distant observer has lost its red component, producing the intense blue the telescopes record. Uranus, Neptune's neighbor in the outer solar system, also contains methane and also appears blue-green. The two planets are similar in size and composition, but Neptune is a distinctly deeper, richer blue. Scientists spent years trying to explain the difference. A partial answer emerged from detailed spectral analysis. Both planets have methane, but their atmospheric structures differ in ways that affect how light scatters. A haze layer at high altitude in Uranus's atmosphere appears to add a grayish tint that lightens its overall color toward blue-green. Neptune's upper atmosphere has less of this haze or a different distribution, allowing the deeper blue from methane absorption to dominate. The photochemical processes connected to Neptune's cloud story also affect this color. The same ultraviolet-driven reactions that produce cloud seeds generate haze particles in the upper atmosphere. Changes in solar activity change the production rate of those haze particles. A change in haze concentration would subtly affect how Neptune's color appears to precise instruments. The same solar cycle driving Neptune's cloud disappearance may also be slowly changing the planet's observable color at a level that spectral analysis can detect. The color of a planet, it turns out, is not just aesthetic information. It is a chemical record encoding information about methane concentration, haze particle density, and atmospheric structure at different altitudes. Reading that color carefully is another way to track the same changes that thermal infrared measurements detect as temperature variations. All of this, the temperature crisis, the cloud disappearance, the polar spike, the color changes, matters far beyond Neptune itself. Astronomers trying to understand planets around other stars face a fundamental limitation. They cannot visit those worlds. They cannot deploy instruments on them. They cannot fly spacecraft past them. Everything known about exoplanets comes from the faint signals that distant worlds leave on the light from their parent stars. The most common planet type discovered orbiting other stars is called a sub-Neptune, a planet larger than Earth but smaller than Neptune. These worlds appear around roughly 30 to 50% of Sun-like stars. Based on data from the Kepler and TESS space telescopes, they appear to be the dominant planet type in the galaxy by number. Our solar system has none. Earth is a rocky planet. Jupiter is a gas giant. Uranus and Neptune are ice giants at the larger end of the sub-Neptune size range. Whatever process produces sub-Neptunes in such abundance around other stars apparently did not produce them here. We live in a system that lacks the most common planet type in the universe. Because we have none locally to study up close, Neptune is the best available template. When astronomers try to predict what the atmosphere of a sub-Neptune exoplanet looks like, how thick it is, what gases it contains, how its temperature varies with altitude, they draw heavily on ice giant science. Neptune is the model. If that model is wrong, every prediction built from it is wrong too. Neptune has now shown that its atmosphere behaves in ways that existing models cannot predict. The stratospheric cooling of 14 degrees during summer cannot be fully explained. The polar spike of 20 degrees in 2 years has no confirmed mechanism. The cloud disappearance driven by solar photochemistry across 2.8 billion miles was not expected. The models are broken in ways scientists are still mapping. Using a broken Neptune model to interpret the atmospheric spectra of exoplanets orbiting distant stars introduces errors at every step of the analysis. If scientists misidentify atmospheric features in an exoplanet spectrum because their baseline understanding of how ice giant atmospheres behave is incomplete, they could misclassify the planet's composition, temperature structure, or even its potential to support liquid water. This is not a theoretical risk. Researchers using the James Webb Space Telescope to analyze exoplanet atmospheres are doing exactly this kind of work right now. The interpretive frameworks they use draw on planetary models that Neptune has just demonstrated to be incomplete. Neptune has essentially issued a correction to the instruction manual for reading planetary atmospheres. The correction is incomplete because scientists do not yet fully understand what Neptune is showing them. But the existence of the gap is now undeniable. When Neptune completed its first observed year in 2011, 165 Earth years after discovery, the people who first found it were long dead. The people who built the instruments that watched it complete that orbit had not yet been born when discovery was made. The planet moves on timescales that swallow human generations whole and entire scientific careers in a single season. Scientists observed Neptune cooling globally during summer and found no confirmed cause. They observed it spiking 20 degrees at one pole while the rest of the planet kept cooling and found no confirmed connection between the two events. They observed every cloud disappear across a 26-year photographic record and traced it to solar photochemistry operating across 2.8 billion miles of space. Each of those discoveries came from sustained, coordinated observation campaigns running over years and decades. Building data sets one image at a time. Two chemical systems operating in Neptune's atmosphere deserve special attention as the investigation moves forward. The first is methane. Methane's role in Neptune's color and cloud formation is well established. Its role in the planet's thermal balance is less discussed but equally important. Methane in the stratosphere absorbs infrared radiation and re-emits it. The net thermal effect depends on altitude and concentration. At certain altitudes, methane warms the surrounding air by absorbing incoming solar infrared energy. At other altitudes, methane contributes to cooling by emitting infrared heat outward into space more efficiently than surrounding gases. The balance between methane's warming and cooling effects is sensitive to concentration. A relatively small change in how much methane exists at a particular altitude could shift the stratosphere from a net heat-retaining layer to a net heat-releasing one. If methane concentrations at key stratospheric altitudes decreased between 2003 and 2018, the stratosphere would have become more efficient at radiating heat into space, which would explain the cooling trend. The same photochemical reactions that produce cloud seeds also destroy methane. Ultraviolet radiation breaks methane molecules apart, turning them into more complex compounds that drift out of the stratosphere over time. The rate of this destruction depends on solar ultraviolet intensity. Understanding how this chain of reactions evolved during the observation period requires chemical composition measurements that only Webb and future instruments can provide. The second is molecular hydrogen. Hydrogen is the dominant component of Neptune's atmosphere and controls the basic thermal properties of the atmospheric gas. Hydrogen can exist in two forms that differ in how the two atoms in each molecule spin relative to each other. These forms are called orthohydrogen and parahydrogen. The two forms absorb and emit heat differently at very low temperatures. The balance between them in Neptune's atmosphere affects how efficiently the stratosphere radiates heat into space. Temperature itself influences which form of hydrogen is more stable. As Neptune's stratosphere cools, the balance between orthohydrogen and parahydrogen shifts. This shift changes the stratosphere's radiative properties, potentially causing it to radiate heat even more efficiently, which would drive further cooling. A self-reinforcing cooling loop where initial cooling drives a hydrogen state change that drives more cooling could explain both the speed and the persistence of the temperature drop observed between 2003 and 2018. This feedback mechanism is physically grounded and has been discussed in the scientific literature as a potential contributor to the stratospheric cooling. Whether it is the primary driver, a contributing factor, or a minor effect remains unknown. The measurements needed to test it require precise spectroscopic observations of the orthohydrogen to parahydrogen ratio across different latitudes and over time. Webb's infrared spectrometers may be capable of detecting this ratio. The data may already exist in Webb's archived observations, waiting for analysis. The answer to Neptune's cooling mystery may already be recorded, just has not been extracted yet. There is also the polar spike timing puzzle to keep in mind. The South Pole spike happened between 2018 and 2020. The global stratospheric cooling reached its minimum around 2018. Both events peaked at roughly the same time. A connection between these two, one cooling globally and one warming locally at almost exactly the same moment, seems too precise for coincidence. Some planetary scientists have proposed that the global cooling may have driven atmospheric circulation, changes that concentrated heat at the pole, a kind of thermal redistribution where energy removed from the global stratosphere was funneled into the polar region. This mechanism would require atmospheric dynamics that existing models do not capture. It remains speculative, but it points toward an architecture in Neptune's atmospheric system, one where solar input, internal heat, atmospheric chemistry, and large-scale circulation interact in ways that produce behaviors far more complex than any single factor can explain. The honest scientific position is that the full picture is not yet drawn. The data is real. The temperature record is confirmed. The solar cloud correlation is statistically meaningful and mechanistically grounded. The polar spike is documented with precision. The cloud disappearance is established across a 26-year archive. What remains is the deeper architecture of cause and effect, connecting all three events to each other and to the mechanisms driving them. Neptune has been there for 4.5 billion years. Humans have been paying serious, sustained, systematic attention for less than 40. The gap between those numbers is where the remaining mysteries live. Every time scientists have assumed the outer solar system was stable, predictable, and behaving according to understood rules, the outer solar system has offered a correction. Saturn's storm systems that erupt and vanish. Jupiter's interior dynamics that drive atmospheric behavior nobody predicted. Uranus's extreme axial tilt and the lopsided thermal signature it creates. And now Neptune, doing three dramatic and simultaneous things over a single human generation of observation that broke every model available at the time they happened. The solar system is not a finished picture. It is an ongoing process. Planets at its edge behave on timescales longer than scientific careers and through mechanisms that require decades of sustained observation to detect. What Neptune has shown specifically is that even a planet receiving 900 times less solar energy than Earth remains sensitive to the Sun's 11-year rhythm in ways that show up visibly in its cloud cover. That the distance of 2.8 billion miles does not dilute all solar influence to irrelevance. That the models built on Earth-based atmospheric physics and gas giant observations are missing key mechanisms specific to ice giant behavior. And that those missing mechanisms matter for every sub-Neptune planet orbiting every Sun-like star across the galaxy, because Neptune is the template astronomers use when trying to read those distant atmospheres. Fixing the template requires understanding Neptune. Understanding Neptune requires years more of Webb observations, eventually supplemented by a dedicated mission to the ice giants. A mission to Uranus or Neptune has been among the top priorities in the most recent Planetary Science Decadal Survey, the document the scientific community uses to set priorities for the coming decade of exploration. A dedicated ice giant orbiter, the kind of mission that would follow a planet through multiple seasons rather than flying past it in a single afternoon, would transform what scientists can know about these worlds. Until that mission arrives, and potentially for decades after it does, Webb will be the primary tool advancing Neptune science. 20 years of Webb observations covering roughly half of one Neptune season is the most sustained thermal and chemical portrait of the planet ever assembled. The instruments are running. The data is accumulating. The answers are somewhere in it. What Neptune has already shown is enough to reset expectations for the entire class of worlds it represents. A planet that had been observed for more than a century, flown past by a spacecraft, watched through the best ground and space telescopes humans ever built, and included in thousands of planetary models, still managed to surprise the scientific community with changes that no one predicted and that remain only partially explained. That is not a failure of science. That is science working. The models were the best available with the data in hand. The observations that broke them are now the foundation for better ones. The questions Neptune raised in the data from 2003 to 2020 are sharp, specific, and physically grounded. They have answers. Finding those answers will take time, coordinated effort, new instruments, and the particular kind of patience that planetary science demands, the willingness to watch a planet move through seasons that outlast entire scientific careers, trusting that the data being collected today will someday be the archive that reveals the pattern. The James Webb Space Telescope is staring at that data right now. If what Neptune is doing sits with you the way it should, take a moment with it. A planet nearly 3 billion miles away, largely ignored for most of human history, receiving a tiny fraction of the sunlight Earth gets, silently cooling and spiking and stripping itself of clouds, while existing models said none of it should happen at that speed or scale. And the implications of understanding it correctly reach all the way to the billions of similar worlds scattered across the galaxy, worlds we will never visit, worlds we can only read through the faint signals they leave on starlight, worlds we interpret through models that Neptune has just shown us need rebuilding. If you find that kind of science worth following, subscribe and stay with it. The next chapter of Neptune's story is being written in Webb's data archives right now, and when the analysis catches up to what the instruments are seeing, what comes out of it will likely be worth the wait. To fully appreciate the significance of what Neptune revealed between 2003 and 2020, it helps to situate it within the broader history of how humans have understood the outer solar system. For most of the 20th century, the outer planets existed in the scientific imagination as distant, cold, and fundamentally static. Jupiter was alive with storms and radiation belts. Saturn was ringed and complex. But the ice giants, Uranus and Neptune, sat so far out that scientists expected them to behave like frozen snapshots, worlds that changed on geological timescales, if they changed at all. That assumption was not unreasonable given the available data. Uranus had been observed for over 2 centuries without revealing any behavior that demanded a revision of the basic frozen world model. Neptune, harder to observe by any instrument available through most of the 20th century, offered even fewer surprises. The assumption held, what Voyager 2 showed in 1989 should have prompted a faster revision. A planet with the fastest winds in the solar system, storm systems the size of Earth, rapidly changing cloud features, and an internal heat source that radiated more than twice the energy it received from the Sun is not behaving like a static frozen snapshot. It is a dynamic, energetically driven system whose behavior the available models were not capturing at the level of detail that the data warranted. But Voyager 2 was a single visit, a snapshot, not a film. Scientists took the images, catalogued the observations, updated the models somewhat, and then returned to watching from a distance. The sense that Neptune was fundamentally understood persisted through the 1990s. The models did not break dramatically because the follow-up observation capability was not refined enough to reveal where they were breaking quietly. The 2003 monitoring campaign changed that. It was the first attempt to build a long-term continuous thermal portrait of Neptune to watch the planet systematically across years and then decades. And what it found, slowly, image by image across a 15-year arc, was a planet that had been quietly violating its own models for the entire time scientists had been building those models. The violation was not visible in any single observation. No scientist looking at Neptune in any given year between 2003 and 2015 would have flagged a crisis. Each year looked like a quiet, cold, distant planet doing what distant, cold planets do. The crisis was in the pattern, in the direction the trend line was moving over years and then decades. And the pattern was only visible once someone assembled enough data to see the full arc. This is a recurring challenge in outer planet science. The phenomena that matter most operate on timescales that dwarf any individual observation campaign. A weather pattern on Neptune might unfold over 30 years. A climate oscillation might span an entire Neptune season of 40 Earth years. A scientist with a standard career from doctoral student to retirement might devote their professional life to Neptune and still not live to see a complete seasonal cycle. The science demands a kind of institutional continuity that is difficult to maintain in any funding environment. The Neptune monitoring campaign was maintained through exactly this kind of sustained institutional commitment. It was expensive. It required competing for telescope time at oversubscribed observatories year after year, building and maintaining a data reduction pipeline that evolved as instruments improved, and coordinating a team across multiple countries across 2 decades. The result was a dataset that, when finally analyzed comprehensively, revealed changes that no single year of observation would have shown, and that fundamentally altered the scientific community's understanding of this world. The Great Dark Spot and its disappearance tell a parallel story that deserves more attention in this context. When Voyager 2 photographed Neptune in 1989, it captured an enormous rotating storm system in the southern hemisphere. Oval in shape and roughly the size of the entire Earth, scientists named it the Great Dark Spot. It was Neptune's answer to Jupiter's Great Red Spot, a massive atmospheric vortex that had apparently persisted for centuries. The comparison was natural. Both were large, obvious, rotating storm features dominating their hemisphere's appearance. 5 years later, Hubble looked for the Great Dark Spot. It was gone. A storm large enough to contain Earth had simply dissolved in less than 5 years. In its place, a new dark spot had formed in Neptune's northern hemisphere. This northern storm had not been there when Voyager 2 flew past. It had appeared between 1989 and 1994. Jupiter's Great Red Spot has persisted for at least 350 years, possibly much longer. Saturn's storm systems are long-lived. Neptune's storms seem to appear and vanish on timescales of a few years. Large, powerful, conspicuous, then gone, replaced by new ones at different latitudes. The mechanism driving this rapid turnover connects to the same atmospheric dynamics that make Neptune so difficult to model. The interplay between internal heat, rapid rotation, cold upper atmosphere, and fast wind systems create storm structures that form and dissolve at speeds that have no parallel on other outer planets. Scientists believe Neptune's dark spots form when material from the lower atmosphere rises into the upper atmosphere and gets organized into a rotating vortex by the planet's wind patterns. The spots are disruptions in the bright methane cloud layer, revealing the darker atmosphere below. When conditions change, perhaps driven by shifts in thermal structure or wind patterns, the organizing force sustaining the vortex weakens and the storm breaks apart. The speed with which the Great Dark Spot disappeared before Hubble arrived demonstrates how quickly Neptune can reorganize its entire visible appearance. That capacity for rapid reorganization is directly relevant to the temperature crisis documented between 2003 and 2020. If Neptune's visible atmosphere can completely restructure itself in 5 years, the changes in cloud cover and stratospheric temperature documented over 15 years are perhaps less surprising than they initially appeared. Neptune changes fast, faster than any model built before the monitoring campaign had anticipated. The changes are real, sustained, and large, and they have consequences that reach across the solar system and beyond. The specific mechanism of photochemical cloud seeding, confirmed through the solar cycle correlation, is the most important discovery to emerge from the 2003 to 2020 observation period for reasons that extend well beyond Neptune itself. The discovery that a planet receiving 900 times less solar energy than Earth remains sensitive to the Sun's 11-year ultraviolet cycle in ways that directly control its cloud formation is a finding that recalibrates how scientists think about the relationship between stellar activity and planetary atmospheres at any distance. On Earth, the connection between the solar cycle and climate is a topic of active and sometimes contentious research. The Sun's 11-year rhythm produces measurable effects on Earth's upper atmosphere, including changes in ozone concentration, stratospheric temperature, and the extent of the polar vortex. Whether those effects propagate downward into the lower atmosphere in ways that influence surface temperatures and regional weather patterns is a question scientists have studied extensively. The evidence for a direct solar cycle influence on Earth's surface climate is contested and considered relatively modest compared to other climate drivers. On Neptune, the solar cycle signal is not modest. It is large enough to turn cloud formation on and off across the whole planet over roughly a decade. A planet 2.8 billion miles from the Sun is more sensitive to the solar cycle in terms of cloud formation than any model of ice giant atmospheric chemistry had predicted. That finding has immediate implications for every exoplanet that orbits a star with its own activity cycle, which is essentially all of them. Stars vary. They cycle through periods of higher and lower ultraviolet output on various timescales. If that ultraviolet variation drives photochemical cloud seeding in ice giant atmospheres the way it apparently does on Neptune, then the cloud cover of sub-Neptune exoplanets may fluctuate systematically with the activity cycles of their host stars. This matters for atmospheric observations. When astronomers observe an exoplanet atmosphere by measuring how the starlight spectrum changes as the planet transits across its star's face, they are taking a snapshot. That snapshot captures the atmospheric composition and cloud cover at one moment in time. If that cloud cover varies significantly over an 11-year stellar activity cycle, a single snapshot may not be representative of the planet's average state. Scientists might observe a planet during a cloud minimum phase and conclude its atmosphere is mostly clear, then observe it again during a cloud maximum phase and find it heavily overcast, and interpret the difference as evidence of some other physical change, rather than recognizing it as a normal oscillation driven by the star's activity cycle. Neptune has demonstrated that this kind of oscillation is real and large-scale in at least one ice giant atmosphere. It has also demonstrated that the mechanism behind it, photochemical cloud seeding driven by ultraviolet radiation, operates across distances and energy levels that planetary scientists had not anticipated, including this mechanism in models of exoplanet. Atmospheres is now a scientific priority rather than an optional refinement. The implications compound when you remember that sub-Neptunes are the most common planet type in the galaxy. If a significant fraction of those worlds have ice, giant-like atmospheres where photochemical cloud seeding operates, the stellar activity cycles of their host stars would produce systematic variations in their cloud cover. Atmospheric chemistry and potentially surface temperatures if any surface exists at the pressures relevant to those worlds. Those variations would propagate into the observational data astronomers collect. Understanding Neptune well enough to correctly model its cloud photochemistry is not a narrow, specialized interest in one distant world. It is a prerequisite for correctly interpreting data from billions of planets across the galaxy. The question of how long Neptune's cloudless state will persist adds another dimension to the investigation. The solar minimum of 2019 and 2020 was among the deepest in the modern observation record. As the Sun moved into its next solar maximum cycle, ultraviolet output began recovering. The photochemical cloud seeding mechanism should have resumed, gradually rebuilding the supply of seed particles in Neptune's upper atmosphere and eventually allowing cloud formation to restart. Scientists watching Neptune through Webb and ground-based telescopes in the period following 2020 are in a position to test this prediction directly. If clouds are returning on a schedule consistent with the solar cycle correlation, that would confirm the photochemical model with a precision that the historical data alone could not provide. If clouds are returning faster than expected, it might suggest that the stratospheric thermal changes also played a role in suppressing cloud formation during the minimum, and that the thermal recovery is helping the cloud recovery. If clouds are recovering more slowly than the solar cycle alone would predict, it might indicate that additional factors are operating, perhaps changes in atmospheric chemistry that persist after the solar minimum passed. This test is ongoing. The results of it will be among the most significant Contributions to Neptune atmospheric science. In the coming years, the polar spike also remains unresolved, in ways that should occupy scientific attention for years. The 20-degree warming at the South Pole between 2018 and 2020 was not predicted by any model. It was not explained by any confirmed mechanism after it happened. It left a set of specific questions that the next generation of observations is positioned to address. The first question is whether the polar spike was a one-time event or the beginning of a sustained polar warming trend. The South Pole is still in summer. It has been tilting toward the sun since around 2005 and will continue doing so for approximately another 2 to 3 decades. If the spike was driven by a threshold release of stored solar energy, the pole might now be settling back toward the global temperature average. If it was driven by a structural change in the polar atmosphere, the elevated temperatures might persist or even increase as summer continues. Webb observations of the South Polar region over the next decade will reveal which scenario is occurring. The second question is whether the global stratospheric cooling trend that produced the 14-degree drop between 2003 and 2018 has continued, reversed, or plateaued after 2018. The solar minimum of 2019 and 2020 might have driven the stratosphere to its coldest point yet, consistent with the solar cycle correlation, before a recovery began as solar activity increased. Alternatively, the cooling trend might have a timescale longer than the solar cycle and might still be running. The post-2020 thermal data is the most urgent piece of the Neptune puzzle. The third question is what the polar spike tells scientists about the deeper thermal structure of Neptune's atmosphere. A localized 20-degree warming at a single pole while the rest of the planet maintains a 15-year cooling trend implies a degree of thermal isolation between atmospheric regions that existing models did not anticipate. Atmospheric circulation should tend to smooth out temperature differences over time. Sharp boundaries between extreme temperatures require sustained mechanisms to maintain them against the pressure-driven tendency for air masses to mix. What is maintaining the sharp boundary between the warm South Pole and the cooler surrounding atmosphere is unknown. The atmospheric dynamics required to explain it would tell scientists something important about how Neptune's circulation actually operates versus how the models assumed it does. The Voyager 2 flyby in 1989 gave scientists 36 hours of Neptune science. 36 hours to observe a planet from close range after a 12-year journey to reach it before the spacecraft continued on its trajectory out of the solar system. In those 36 hours, scientists gathered more data about Neptune than had been collected in the entire century and a half since its discovery. They found the Great Dark Spot, documented the wind speeds, confirmed the internal heat excess, photographed the ring arcs and the moons, and captured images that still define the public image of the planet. Then the spacecraft left, and the scientists went back to observing from billions of miles away. Everything discovered since then, including the global cooling, the polar spike, the cloud disappearance, the solar cycle correlation, all of it was extracted from signals crossing 2.8 billion miles of space, detected by instruments at the edge of their sensitivity limits, processed through reduction pipelines, built to remove noise from signals faint enough to be invisible. To any less precise detector, a dedicated ice giant orbiter would transform the science the way Cassini transformed understanding of Saturn and its moons. Cassini orbited Saturn for 13 years, watching it across multiple seasons, tracking the dynamics of its rings and atmosphere in detail that flyby science could never approach. An orbiter around Neptune would watch the planet through most of a full Neptune summer, documenting the thermal evolution of the South Polar region as summer progresses, tracking the chemistry of the stratosphere through Webb-quality spectral observations made from orbit rather than from billions of miles away, and following the cloud recovery as the solar cycle turned from minimum toward maximum. The Planetary Science Decadal Survey completed, in 2023 identified a Uranus orbiter with an atmospheric probe as its top priority for flagship missions. Neptune was a close second. The reasons are exactly those that Neptune's recent behavior has made urgent. The ice giants are the least explored class of planets in the solar system. They are the most common planet type in the galaxy, and the models used to understand them have just been shown to be missing key mechanisms. The political and funding landscape for large planetary science missions is complicated and evolving. A flagship mission to the outer solar system requires years of development. The political will to sustain funding across multiple election cycles, and the engineering challenges of surviving a journey to 2.8 billion miles. The timeline for a Neptune orbiter, even if approved soon, would stretch across decades. The spacecraft would not arrive at Neptune before the 2050s at the earliest, given the travel time involved. In that window, Webb's sustained observations represent the best available bridge between the 1989 flyby science and whatever dedicated orbital science eventually becomes possible. Every year of Webb data on Neptune adds to a record that, over time, will reveal the full structure of the atmospheric changes that began in 2003. A complete answer may take decades, but the tools to find it are accumulating data now. The solar system has been revealing its complexity in exactly this pattern throughout the history of planetary science. Each new instrument uncovers behaviors the previous generation of models had not anticipated. Each new mission to a previously unexplored or underexplored world returns data that forces revisions at a fundamental level. The outer solar system has been particularly resistant to simple models. Jupiter's atmosphere does things that Earth-based, fluid dynamic simulations struggled to reproduce for decades. Saturn's rings turn out to be geologically young and actively evolving in ways that challenged models built around the assumption of ring stability. Pluto, once dismissed as a frozen, geologically dead rock at the edge of the solar system, was found by New Horizons in 2015 to have active geology, ice mountains, nitrogen glaciers, and a complex atmosphere. Neptune has now added its voice to that chorus of corrections. A planet at the edge of the known solar system, receiving almost no sunlight, orbiting so far from the Sun that a year there outlasts human generations, changed its global temperature, its polar temperature, and its entire visible cloud cover in ways that no model anticipated, during a 15-year window of observation that represents a tiny fraction of a single Neptune season. The scientific community's response to that has been what it should be. Not a claim that everything is now understood, but a systematic effort to build better instruments, collect more data, and develop models that incorporate the mechanisms Neptune has exposed as missing. The solar cycle connection to cloud photochemistry is now a confirmed mechanism. The role of the orthohydrogen to parahydrogen ratio in stratospheric cooling is now an active research question, with Webb capable of delivering relevant measurements. The connection between the global cooling and the polar spike is now a formally recognized puzzle whose solution may require dynamics that no current model captures. These are sharp, specific, physically grounded questions. Science makes progress on sharp questions. And while the answers are still being assembled, Neptune keeps doing what it has always done. Operating on its own timescale, responding to influences scientists are still learning to map, carrying processes in its interior and atmosphere that humans have so far only glimpsed. It completes each slow orbit indifferent to the instruments pointed at it from billions of miles away, indifferent to the models built about it and broken by its behavior, indifferent to the debates in scientific journals about what mechanism is responsible for what observation. Neptune does not announce itself. It sends no beacon. It remains, as it always has, the most distant major planet, the one that took the longest to find, the one that is hardest to reach and hardest to read, and the one that keeps finding new ways to demonstrate how much remains unknown about worlds that orbit far from any star's warmth. The next chapter is being written in data. Webb is collecting it. Analysts are working through it. When they find what Neptune's chemical fingerprint reveals about the mechanisms behind 3 simultaneous atmospheric crises that broke every model available to science when they happened, the answer will matter, not just for understanding one cold blue planet at the edge of the solar system. It will matter for understanding the billions of similar worlds orbiting stars across the entire galaxy, most of which will never be visited by anything humans build, and all of which can only be understood through the quality of the models scientists develop right here. Starting with the one closest planet that fits the template. Neptune has been there for 4.5 billion years. It will keep doing what it does for billions more. The question is how much of it scientists will understand before the next generation of instruments looks back at this period and wonders how the previous generation missed what. In retrospect, may have been completely obvious. That is the position every generation of scientists finds itself in. The models of their predecessors always look insufficient in the light of better data. The models scientists build today will look insufficient to their successors. But the data they collect now, the observations they make, the patterns they document across years and decades, those become the foundation from which the next revision begins. The 95 thermal infrared images collected across 20 years of sustained observation revealed a planet nobody predicted. The Webb observations accumulating now will reveal the mechanism behind what those images showed. The orbiter that eventually reaches Neptune will reveal what Webb, watching from the inside of the solar system, could not. Science is not a destination. It is a direction. And Neptune, sitting at the edge of everything humans have ever explored directly, is pointing it further outward. There is a detail about Neptune's discovery that rarely makes it into the standard telling, but that changes how the story feels. After the mathematician John Couch Adams in England and the mathematician Urbain Le Verrier in France independently calculated where the hidden planet had to be, using only the orbital anomalies of Uranus as their evidence, the two men had very different experiences getting astronomers to actually look. Adams finished his calculations first, in 1845. He brought them to the Astronomer Royal of England, George Airy, and to the director of the Cambridge Observatory, James Chalice. Neither man prioritized the search. Airy had doubts about whether a perturbation in a planet's orbit could be used to calculate the mass and position of an unseen body. Chalice began searching, but without urgency. He observed the region of sky Adams had identified on multiple nights and actually recorded Neptune in his telescope logs without identifying it as a planet, because he was comparing observations to outdated star charts. Neptune appeared in Chalice's own observational record before Le Verrier's calculation led to the discovery in Berlin. If the Cambridge search had been conducted with proper star charts and appropriate urgency, England would have been credited with the discovery. Instead, Le Verrier, whose calculations were completed months later, sent his predicted coordinates directly to Johann Galle at the Berlin Observatory. Galle had access to a recently completed detailed chart of that exact region of sky. He pointed his telescope at Le Verrier's predicted position and found Neptune within the first hour of observation, within less than 1 degree of the predicted location. The speed and precision of that discovery in Berlin, using Le Verrier's coordinates, became the confirmation that mathematical prediction of an unseen planet was possible. It changed planetary science fundamentally. The success demonstrated that gravity's influence could be traced backward through observational anomalies to reveal the mass and position of an unseen body. The same principle was later applied in the search for Pluto, discovered in 1930 based on predicted perturbations of Neptune's orbit, though the reasoning turned out to be partly coincidental. And it underlies modern techniques for detecting exoplanets through gravitational perturbations in multi-planet systems. But the episode also demonstrates something about how science actually progresses. The correct answer was available to English astronomers before Le Verrier finished his calculation. The star charts were unavailable in Cambridge at the right moment. The institutional urgency was insufficient. The discovery went to the team that had both the calculation and the infrastructure to act on it immediately. Neptune's history is full of moments like this. The planet appearing on an earlier astronomer's star chart as a background star, sitting in the data for months before anyone identified it as moving. The Voyager 2 flyby capturing 36 hours of close-range observations that immediately revealed the Great Dark Spot, only for Hubble to find that storm gone just 5 years later. The cooling trend running through 15 years of thermal infrared measurements before anyone assembled enough of the data to see the full arc. This is a pattern. Neptune reveals itself in retrospect, through accumulated records rather than dramatic individual discoveries. The planet's character, its habit of sitting in plain sight while remaining completely mysterious, runs through the entire history of its study. It continues today. The chemical fingerprints that explain the cooling, the polar spike, the cloud disappearance may already be present in Webb's archived observations. The answer may be sitting in data that has been collected but not yet fully analyzed. Neptune waiting, as it always has, to be recognized as something more than background noise. The size of Neptune relative to Earth is worth holding in mind while considering how its atmosphere changed between 2003 and 2020. Neptune's volume is roughly 58 times Earth's volume. If you hollowed Neptune out and tried to fill it with copies of Earth, you would need 58 of them. Its diameter is nearly 4 times Earth's diameter. When scientists describe the global stratosphere of Neptune cooling by 14 degrees Fahrenheit over 15 years, they are describing a temperature change across an atmospheric layer that wraps a sphere nearly 4 times wider than Earth and 58 times more voluminous. Energy that left Neptune's stratosphere during that cooling period is enormous by any intuitive measure. Warming a mass of gas by 1 degree Fahrenheit requires a specific amount of energy. The mass of gas in Neptune's stratosphere, distributed across a volume dwarfing Earth, is vast. Cooling all of it by 14 degrees while summer was adding solar energy to the system means an active and sustained removal of heat energy at a scale that exceeds the total solar energy input Neptune receives over significant periods. Neptune's internal heat source, radiating more than twice the energy the planet receives from the Sun, provides the reservoir from which this kind of energy movement could draw. But the stratosphere is physically separated from the interior by thousands of kilometers of atmospheric layers. The mechanism that would transport internal heat all the way up to stratospheric altitudes and then somehow turn off or reverse during a summer when solar input was increasing is not established. What is established is that the stratosphere lost a lot of energy over 15 years. Where that energy went is one of the unanswered questions. The scale of Neptune also puts the polar spike in a different perspective. A 20-degree temperature increase at the south pole of Neptune is a 20-degree increase across a polar atmospheric region comparable in area to multiple Earths laid side by side. The amount of heat energy that had to arrive at or concentrate in that polar region to produce a 20-degree warming in 2 years is substantial, and it arrived at a single location on a planet where the rest of the stratosphere was simultaneously at its coldest point in the modern observation record. Understanding where that energy came from, whether it was accumulated solar energy stored in the polar atmosphere over the decades of summer, whether it was internal heat channeled upward by unusual convective patterns, whether it was heat transferred from the global stratosphere through a circulation mechanism no model had included, requires the kind of chemical and thermal profiling that only Webb's spectroscopic instruments can provide from Earth's neighborhood. Neptune's moons add another layer of complexity to the system that rarely receives adequate attention in discussions of the planet's temperature crisis. Neptune has 14 known moons. The largest and most unusual is Triton, a world large enough that it would qualify as a dwarf planet if it orbited the Sun independently. Triton is roughly 80% the diameter of Earth's moon. It orbits Neptune in the opposite direction from the planet's rotation, a retrograde orbit that strongly suggests it was captured from somewhere else rather than forming in place around Neptune. A retrograde orbit is gravitationally unstable over very long timescales. Tidal forces from Neptune are slowly pulling Triton inward. Astronomers estimate that in roughly 3.5 billion years, Triton will spiral close enough to Neptune that tidal forces will tear it apart, creating a ring system that might rival Saturn's in breadth and brightness. Triton's surface, when Voyager 2 flew past in 1989, was one of the most actively strange things in the solar system. Nitrogen geysers erupting from the surface. A cryovolcanic landscape covered in pinkish organic material. Temperatures on the surface measured at negative 390 degrees Fahrenheit, among the coldest surface temperatures recorded anywhere in the solar system. And yet active geological processes, plumes of nitrogen gas erupting kilometers into the thin atmosphere. The source of Triton's geysers remains debated. Some researchers think they are powered by solar heating of transparent surface nitrogen ice, which absorbs sunlight internally and builds pressure until it vents. Others think internal heating from Triton's continuing orbital decay and the tidal stresses it creates might contribute. Either way, Triton is not a dead frozen rock. It is an active world with its own processes that Voyager 2 observed for only a few hours, before moving on Triton's interactions with Neptune's magnetosphere and its tidal relationship with the planet contribute to the broader dynamical environment of the Neptune system. Whether those interactions play any role in Neptune's atmospheric behavior is not established. But in a system as dynamically complex as Neptune, where every other feature has turned out to be more connected to other features than simple models predicted, assuming Triton is irrelevant to the atmospheric story without investigation seems premature. The magnetosphere of Neptune is itself unusual. Most planets in the solar system have magnetic fields that are roughly aligned with their rotation axes. Earth's magnetic north pole sits close to the geographic north pole. The field tilts away from the rotation axis by about 11 degrees. Saturn and Jupiter have similar alignments. Neptune's magnetic field is tilted about 47 degrees away from the rotation axis, and the center of the magnetic field is displaced significantly from the center of the planet itself. The result is a magnetic field geometry that does not resemble any other planets in the solar system. This unusual field geometry creates a magnetosphere that wobbles dramatically as the planet rotates, sweeping its field through a complex three-dimensional pattern rather than the relatively symmetric bubble structure seen around other planets. How this unusual geometry affects the way charged particles from the solar wind interact with Neptune's upper atmosphere, and whether those interactions contribute to the photochemical processes that drive cloud formation and stratospheric chemistry, is not fully understood. The connection between magnetospheric dynamics and stratospheric chemistry on Neptune represents another poorly mapped piece of the overall system. Understanding Neptune completely, if that is even a finite goal given the planet's complexity, requires accounting for how the magnetic field, the moons, the ring system, the internal heat source, the solar cycle connection, the atmospheric chemistry, and the large-scale circulation all interact with each other. Each of those components has been studied in some isolation. How they operate as a coupled system is a question that only sustained, comprehensive observation can address. What the 2003 to 2020 data revealed is not just specific surprises about specific atmospheric changes. It revealed that Neptune's atmospheric system is coupled to its broader environment, including the solar cycle, in ways that operate across distances and energy levels that planetary models had not accounted for. That coupling is the discovery, not just the cooling or the cloud disappearance or the polar spike individually. Those events are symptoms. The coupling between the Sun's activity cycle and Neptune's atmosphere through ultraviolet photochemistry is the mechanism. And once that mechanism is confirmed to operate on Neptune, the question of where else it operates, on Uranus, on sub-Neptune exoplanets around other stars, On any world with a methane-bearing atmosphere and photochemically active upper layers becomes an organizing question for an entire field. The timeline of Neptune's observation history is worth assembling explicitly because it illustrates how slowly scientific understanding of this world has advanced relative to the complexity the world actually possesses. 1846. Neptune is discovered. Scientists do not yet know its size, mass, composition, or whether it has moons. The discovery itself was a triumph of mathematical prediction, but the physical understanding of the planet is essentially zero. 1846 to 1989. 143 years of ground-based observation. During this period, scientists determine Neptune's approximate size and mass, identify 2 of its moons, and detect evidence of a ring system. They have no close-up images of the planet. They cannot measure its atmospheric temperature directly. They cannot determine its rotation period with confidence. The planet is a blue dot in even the best telescopes of the era. 1989. Voyager 2 flies past. In 36 hours, scientists learn more about Neptune than in the previous 143 years combined. The Great Dark Spot, the fastest winds in the solar system. The moon Triton with its nitrogen geysers. The internal heat excess. The ring arcs. The rotation period. The magnetic field geometry. A complete transformation in scientific understanding of the planet, bought with 12 years of spacecraft travel and 36 hours of proximity. 1989 to 2003. 14 years of ground-based and Hubble observation following the flyby. Scientists watch the Great Dark Spot disappear and a new dark spot form in the northern hemisphere. They track Neptune's cloud features. They refine models based on Voyager 2 data. They begin planning the systematic thermal monitoring campaign that will start in 2003. 2003 to 2020, the monitoring campaign builds the thermal record. The 26-year photographic archive reveals the cloud disappearance. Scientists publish the comprehensive study in 2022 showing global cooling, polar spike, cloud loss, and solar cycle correlation. The models are broken. New research directions open 2021 onward. James Webb Space Telescope begins operations. Neptune is among its early science targets. Webb's infrared spectrometers begin building the chemical portrait of Neptune's atmosphere that could explain the mechanisms behind the thermal crisis. The data is accumulating. This is the full arc of Neptune science in human history. 176 years from discovery to the current frontier of understanding. And the most significant discoveries, the ones that most fundamentally changed scientific understanding of the planet, came in the last 20 years of that arc. The cooling crisis was documented between 2003 and 2020. The solar cycle connection was confirmed in the same period. The polar spike was recorded between 2018 and 2020. None of it was predictable from the models that existed when the monitoring campaign began. This pattern, accelerating discovery as instruments improve and monitoring campaigns mature, is characteristic of outer planet science generally. The outer solar system is not becoming more mysterious as time passes. It is becoming more legible. The mysteries being uncovered now are mysteries that always existed in the data, but were invisible to instruments with less sensitivity, monitoring campaigns of shorter duration, or analysis pipelines not sophisticated enough to extract the signal from the noise. Neptune's cooling crisis existed in the physics of the planet long before anyone could measure it. The solar cycle connection to cloud formation was operating for billions of years before any telescope was pointed at Neptune with the sensitivity to detect it. The polar spike of 20 degrees in 2 years was a real event that happened between 2018 and 2020, but it happened to a planet that scientists had been watching for decades. They almost missed it, not because the instruments were pointed elsewhere, but because recognizing the significance of the spike required the thermal baseline built across the previous 15 years of the monitoring campaign. This is why sustained observation matters more than any single breakthrough. The breakthrough of recognizing Neptune's thermal crisis was built entirely on the foundation of 15 years of systematic data collection. Without that foundation, each year's data would have looked like a quiet, cold, distant planet doing nothing unusual. With the foundation, the pattern became undeniable. The scientific community is now in the position of having identified the questions and begun building the tools to answer them. Webb is collecting chemical fingerprints. The solar cycle is moving toward its next maximum, which will test whether Neptune's clouds recover on the predicted schedule. The thermal data is continuing to accumulate with each season's observation campaign. Ground-based telescopes continue watching. The picture is becoming more detailed with every year. What Neptune represents, beyond its intrinsic scientific interest, is a case study in how science confronts complexity that exceeds its current models. The models are not discarded. They are revised, refined, and rebuilt to incorporate the mechanisms that observation reveals. The process is slow. It requires patience measured in years and careers. But it works. The models that emerge from the reckoning with Neptune's behavior will be better than the ones that existed before. They will be more accurate. They will make better predictions. And when those predictions eventually fail against the next unexpected observation, the process will continue. That is the scientific method operating exactly as it should on exactly the kind of problem it was built to address. A distant, complex, poorly characterized world, behaving in ways that exceed current understanding, observed through instruments at the limits of their sensitivity, slowly yielding its patterns to analysis, revision, and the accumulation of data across decades. Neptune has been there for 4.5 billion years. It has another 4 or 5 billion years ahead of it before the Sun expands into a red giant and fundamentally changes the thermal environment of the outer solar system. On the timescale of the universe, human science has barely begun paying attention. But in the last 20 years, the attention has been sustained enough. The instruments have been precise enough, and the analysis has been careful enough to reveal that this distant blue world has been doing things that matter, not just for understanding one planet, but for understanding the entire class of worlds it represents across billions of star systems. What Webb finds in Neptune's spectrum in the coming years will be worth knowing. What an ice giant orbiter eventually discovers will reshape the field, and what scientists learned between 2003 and 2020 from 95 thermal infrared images collected across 2 decades of coordinated effort pointed at a world 2.8 billion miles away already stands as one of the more significant achievements in the history of planetary science. Not because the mystery was solved, but because the right questions were finally asked. There is one more dimension to Neptune's story that most discussions of the temperature crisis leave underexplored. The question of what Neptune's behavior means for the search for life beyond our solar system is usually framed around whether life could exist on Neptune itself, which it almost certainly cannot given temperatures that would freeze almost any biochemical process and pressures that would crush any known biological structure. But the relevance runs deeper than whether Neptune itself is habitable. It runs through what Neptune teaches us about interpreting distant atmospheres and what that interpretation means for identifying potentially habitable worlds. When astronomers observe an exoplanet atmosphere and try to determine whether it might support liquid water, they look for specific signatures: the presence of water vapor, temperatures in a range that would allow water to exist as a liquid at the planet's surface, an atmosphere thick enough to maintain pressure without being so thick it generates a runaway greenhouse effect, the absence of chemical compositions that would indicate an atmosphere fundamentally hostile to any chemistry that life as we know it requires, many of the worlds being targeted for atmospheric characterization, with Webb as sub-Neptunes. The TRAPPIST-1 system, for example, contains several rocky worlds at potentially habitable distances from their host star, but the sub-Neptune planets found around other stars, more massive than TRAPPIST-1 planets but smaller than Neptune, are interesting targets for a different reason. Some of them might have water-rich atmospheres or ocean surfaces. Determining whether they do requires reading their atmospheric spectra with models that correctly account for how their atmospheres are structured. If those models are built on ice giant atmospheric science, and the ice giant atmospheric science is built on Neptune, and Neptune has just demonstrated that its atmospheric behavior includes mechanisms those models were missing, then the habitability assessments of sub-Neptune exoplanets carry an unknown but potentially significant systematic error. The error does not necessarily mean any planet currently assessed as potentially habitable is actually barren, or that any planet assessed as uninhabitable might turn out to be supportive of life. The relationship is more subtle. It means the confidence intervals on those assessments are wider than they are currently reported to be. Science is honest about uncertainty when the uncertainty is quantified. The systematic uncertainties introduced by using incomplete planetary models are harder to quantify and therefore harder to communicate. Neptune's crisis has made visible a category of systematic error that was always present but previously invisible. Making it visible is the first step toward quantifying and correcting it. That process is now underway. The Neptune atmospheric science community and the exoplanet characterization community are beginning to work more directly together to understand how the gaps exposed in Neptune's models propagate into the error budgets of exoplanet atmospheric analyses. This collaboration matters for the specific goal of finding life. The James Webb Space Telescope was designed in part to answer the question of whether any exoplanet carries chemical signatures consistent with life. Biosignatures, gases like oxygen, methane, nitrous oxide, whose presence in specific combinations would be difficult to explain without biological activity, are the targets of the most ambitious Webb observing programs. As programs are underway, the data is being collected. Interpreting that data correctly requires atmospheric models that accurately represent the physics and chemistry of the planets being observed. Neptune has demonstrated that the current generation of models for ice giant-type atmospheres is missing key mechanisms. Getting those models right before making claims about the presence or absence of biosignatures in distant exoplanet atmospheres is not a minor technical detail. It is a prerequisite for the most important scientific question of the era. Understanding Neptune is understanding the tools we use to read other worlds, and reading other worlds is the path toward knowing whether life is a local phenomenon confined to one pale blue dot in a vast and mostly empty universe, or whether it is a general feature of planets in the right conditions scattered across billions of star systems. Neptune has never been the romantic planet. It is not Saturn with its spectacular rings visible through any small telescope. It is not Mars with its rust-colored surface and canyon systems and polar ice caps that fire the human imagination. It is not Jupiter with its great storm and its hundreds of moons and its role as the solar system's gravitational shield. Neptune sits far out, barely visible, cold beyond imagining by any standard of human experience, orbiting so slowly that the oldest human civilizations were already ancient when it last crossed the point in its orbit where it sits right now, and yet it turns out to matter. It matters for understanding ice giant dynamics. It matters for understanding the most common planet type in the galaxy. It matters for calibrating the models we use to characterize distant worlds. It matters for the search for life. The lesson may be a general one. The things that matter most in science are not always the things that look most significant from a distance. The small anomalies in Uranus's orbit that nobody could explain in the early 19th century mattered enough to predict the existence of an unseen planet and confirm it in a single night. The slight offset in Mercury's orbital precession that Newtonian gravity could not quite account for turned out to require Einstein's general relativity to explain, proving that gravity and space and time are woven together in a way that Newton's framework had not captured. The cosmic microwave background radiation, discovered as unexplained noise in a radio telescope in 1965, turned out to be the afterglow of the Big Bang, the oldest light in the universe. Neptune's temperature anomalies, documented in 95 thermal infrared images collected across 20 years of coordinated observation, are in this tradition. Small signals from a distant planet, 15 years of cooling that should have been warming, 20 degrees of localized heating in 2 years, cloud bands that vanished over a decade and a half and were only noticed when someone looked at the full photographic record at once. These are not dramatic events visible from the outside with the naked eye. They are subtle signals hidden in data revealed by instruments at the limits of their capability, requiring years of sustained attention to recognize for what they are. What they are is a window into a class of atmospheric processes that operate on every ocean planet, every ice giant, every sub-Neptune in every system throughout the galaxy, where a star's activity cycle can reach across billions of miles to drive photochemical reactions in a cold atmosphere. Neptune is not the endpoint of that investigation. It is the beginning of it. The blue world at the edge of the solar system has been keeping its secrets for 4.5 billion years. It will likely keep some of them for as long as humans are doing science. But the ones it has already revealed quietly, in data collected by instruments pushed to their limits by scientists committed to watching long enough to see the pattern, are already changing how the science understands planets that have never been visited and may never be. That is enough. That is more than enough. Science at its best is exactly this. A patient, sustained, collaborative effort to extract the faint signal from the noise, to recognize the pattern in the data, to build models that can fail correctly when the next generation of observations arrives with sharper instruments and a longer baseline. Neptune's thermal crisis is that process working. The answers are still coming. The questions it raised are among the most important in planetary science. And the tools to find those answers are now the best humans have ever built. Neptune waits. The data accumulates. The models improve. The understanding deepens. One image at a time, across the 2.8 billion miles between here and one of the most surprising worlds in the solar system, there is a question scientists rarely ask explicitly, but that underlies the entire Neptune temperature investigation. How confident should any model of a planetary atmosphere be when the planet has been observed for less than 1/4 of one of its seasons? The answer, which Neptune has now empirically demonstrated, is less confident than the field had been behaving. Confidence in a planetary model is built from several sources: theoretical frameworks from physics and chemistry that describe how gases behave under various conditions, observations of similar systems, whether other planets in the solar system or laboratory experiments that recreate relevant conditions, and time series data showing how the system under study actually evolves. For Neptune, the theoretical frameworks were applied from Earth and gas, giant atmospheric science, adapted for ice giant conditions. The observations of similar systems included Uranus, the only other ice giant with any significant observational baseline, and the time series data before the 2003 monitoring campaign were fragmentary, consisting of occasional observations spread across decades without the systematic coverage needed to detect slow trends. The monitoring campaign fixed the last of these problems, at least for the stratospheric temperature. Over 15 years, it built a data set detailed enough to show that the planet was cooling when it should have been warming. That observation forced scientists to confront the limits of the theoretical frameworks and the inadequacy of the similar systems data. The theoretical frameworks turned out to be incomplete in at least one critical way. They did not account for the sensitivity of ice giant cloud formation to the solar ultraviolet cycle operating across 2.8 billion miles. That omission was not the result of carelessness. It was the result of no one having data that would reveal the connection. The data required a 26-year photographic archive analyzed retrospectively. Without that archive, the solar cycle connection to Neptune's clouds could not have been detected. This is the nature of discovery in outer planet science. The phenomena that matter most operate on timescales that require sustained observation to detect, and sustained observation requires institutional commitment that the field does not always receive. Neptune was lucky, in a scientific sense, that someone built the monitoring campaign and maintained it for 2 decades. That luck is not reproducible on demand. It requires a combination of scientific judgment about what questions are worth the investment, institutional support for long-term programs that may not produce dramatic results quickly, and the patience to keep collecting data even when the early years show nothing unexpected. The people who built and maintained the Neptune thermal monitoring campaign between 2003 and 2020 did not know they were going to find what they found. They expected to confirm a warming trend. They found instead a 15-year cooling trend, a 20-degree polar spike, and a solar cycle connection to cloud formation that nobody had anticipated. The discovery came from doing the science correctly, defining a question, building the infrastructure to address it, collecting data systematically, and analyzing it comprehensively when enough had accumulated. The lesson for planetary science broadly is that long-term monitoring campaigns for outer solar system bodies are not optional extras at the margins of the research program. They are the source of the field's most significant discoveries, because the phenomena that most fundamentally challenge existing models operate on timescales that only sustained monitoring can reveal. Neptune has made this argument with data. The field is listening. Meanwhile, the planet itself continues to follow its 4.5 billion-year-old routine. It orbits the Sun at 12,000 miles per hour, carrying its internal heat, its extreme winds, its diamond rain, its partial ring arcs, its retrograde moon Triton, and its complex layered atmosphere through the outer reaches of the solar system. Indifferent to the instruments pointed at it from billions of miles away, its south pole is still in summer. The pole will continue tilting toward the Sun for decades. Whether the temperatures there continue to rise, level off, or fall back toward the global average depends on mechanisms scientists do not yet fully understand. Whether the global stratospheric cooling has continued after 2018 or has reversed depends on data still being collected and analyzed. Whether the clouds have returned as the solar cycle moved toward its next maximum is something Webb's infrared observations are positioned to reveal in detail no previous instrument could achieve. Every year of data narrows the uncertainty. Every observation adds to the record from which the pattern will eventually emerge, with the clarity that 15 years of thermal monitoring eventually achieved for the stratospheric cooling trend. The arc of scientific progress on Neptune is long and slow by any human measure, but it is moving in the direction of understanding. And if there is a final thought that Neptune's story leaves you with, it should be this. The universe does not cooperate with the assumption that what you cannot yet see is simple. Every time science has pointed better instruments at a previously under-examined object, the answer has been more complex than the previous best model predicted. Neptune is no exception. It is perhaps the most current example. A cold, distant, seemingly quiet world at the edge of everything humans have explored directly, running processes that affect the most common planet type in the galaxy, sensitive to the activity of its star across distances that dwarf every concept of far that everyday human experience can supply. If a planet that receives 900 times less sunlight than Earth can still respond to the Sun's 11-year rhythm in ways visible in its cloud cover and potentially in its stratospheric temperature, then the universe is more tightly coupled, more responsive, more connected across larger distances than the models that preceded this discovery had assumed. And if the models were wrong about that for Neptune, they may be wrong about similar couplings on worlds orbiting other stars, where the relationship between stellar activity and atmospheric behavior is assumed to follow the frameworks built on an incomplete understanding of the nearest ice giant we have. The next 20 years of Webb observations will begin to reveal how wrong or how right those frameworks are. The answers will matter for every question about planetary atmospheres that planetary science is currently trying to answer, from the behavior of ice giants in our own solar system to the potential habitability of the billions of sub-Neptunes orbiting stars. Across the Milky Way, Neptune has given scientists a new reason to look more carefully.
That is not panic.
That is the beginning of better science. If this kind of careful look at what science actually knows and does not know about the worlds in our solar system and beyond is worth your time, subscribe and stay with it. The discoveries happening now in planetary science are among the most significant in the field's history, and they are only going to accelerate as the tools get sharper and the observational baselines get longer. Neptune will keep doing what it does. The instruments will keep watching. The data will keep accumulating. And somewhere in that accumulation, the architecture of this planet's atmospheric behavior, in all its coupled complexity, will eventually become legible in a way that changes how we understand not just this world, but every world like it,
Scattered across the universe. That
is what science is for. The specific numbers that came out of the 2022 study that compiled the temperature record deserve a closer look, because they communicate something about Neptune that the words surrounding them sometimes obscure. 14 degrees Fahrenheit of global stratospheric cooling over 15 years. That is the headline finding. But what does 14 degrees mean in the context of Neptune's stratosphere specifically? Neptune's stratospheric temperatures in the regions scientists were measuring hover around minus 340 degrees Fahrenheit near absolute zero. 14 degrees of change on that scale is a proportionally large shift. The stratosphere moved from something like minus 333 degrees to minus 347 degrees, a drop of more than 4% of the temperature above absolute zero in that layer. At the temperatures relevant to ice giant atmospheric chemistry, a 4% change in absolute temperature can meaningfully alter which chemical reactions proceed, at what rate, and in which direction. The 20-degree south polar warming is similarly illuminating when contextualized. The South Pole stratosphere, which was presumably part of the cooling trend through the observation period up to 2018, went from being among the coldest parts of the planet to being the warmest. If the global stratosphere cooled from around minus 333 to minus 347 degrees during that period, and the South Pole then warmed by 20 degrees to something near minus 327 degrees, the pole went from roughly tracking the global
average to sitting roughly 20 degrees warmer than the
globally cooled surrounding atmosphere. The temperature contrast at the boundary between the warm polar stratosphere and the cool surrounding atmosphere is therefore not just 20 degrees in the absolute sense. It is 20 degrees imposed on a system where the non-polar atmosphere had already cooled by 14 degrees from where it started. The boundary between the warmest region and the coolest region of the planet spans more than 30 degrees Fahrenheit of temperature difference, all within the stratosphere of a single planet. On a world where the baseline temperature already sits near absolute zero, this kind of temperature contrast drives atmospheric circulation. The pressure differences associated with such a large temperature gradient would generate wind systems even on a planet not already prone to the fastest sustained winds in the solar system. How Neptune's existing 1,200 mile-per-hour wind patterns interact with a localized warm pole sitting in a sea of unusually cold stratospheric air is a question that requires atmospheric dynamics models far more sophisticated than those currently available for this planet. The 26-year cloud record
adds its own quantitative dimension to the picture.
Scientists measured cloud brightness on a normalized scale across each of the images in the archive. During peak cloud abundance, Neptune's cloud brightness index sat at values reflecting substantial white reflective material across the visible disk. During the cloud minimum of 2019 and 2020, the index collapsed to values consistent with essentially no visible cloud formation. The decline was not linear. It accelerated sharply after 2015 and then steepened again around 2018. The acceleration matches what you would expect from a feedback between the solar cycle and the photochemical cloud seeding mechanism. As solar activity declined toward minimum, ultraviolet output fell. The cloud seed production rate declined. With fewer seeds, cloud formation became less efficient. As clouds thinned, the atmosphere became less reflective, allowing more solar energy to reach deeper layers. Whether this additional solar input contributed to the warming at the South Pole during this period is another piece of the causal architecture that has not been established but cannot be
Ruled out. The fact that cloud
abundance tracks the solar cycle with a 2-year lag is itself a data point that constrains the photochemical mechanism. 2 years is the time it takes for ultraviolet-driven reactions in the upper atmosphere to produce seed particles, for those particles to drift down to cloud-forming altitude, and for methane ice to accumulate on their surfaces and form visible cloud clusters. This 2-year delay is a fingerprint. It tells scientists something specific about the altitudes at which the photochemical reactions occur, the size and settling rate of the seed particles, and the rate of methane ice nucleation at cloud-forming temperatures. Each of those quantities is constrained by the observed lag. This is how science extracts information from timing correlations. The lag is not just an interesting pattern. It is a measurement of multiple physical quantities embedded in a single observational fact. Scientists who know the lag are better positioned to model the full chain of reactions from ultraviolet input to cloud formation and to predict how the chain will respond to variations in solar activity, changes in methane concentration, or shifts in the thermal structure of the atmosphere. The monitoring campaign produced this constraint as a byproduct of building the long-term cloud record. The constraint was invisible in any short-term observation. It only appeared when the full 26-year archive was analyzed with the solar activity record laid alongside. Its science is full of constraints hiding in data that only become visible when the right analysis is applied to the right data set. The Neptune temperature and cloud record is a data set that will almost certainly yield more constraints in future analyses as scientists look at it with new questions informed by what has already been discovered. What Webb adds to this picture is the chemical dimension. Thermal infrared measurements tell you how much heat is being radiated from different altitudes. They tell you temperature. They do not directly tell you what gases are producing those thermal signatures or why those gases are behaving differently than they used to. Webb's spectroscopic capability fills in the chemical side of the picture. By measuring which infrared wavelengths the atmosphere absorbs and emits at different intensities, Webb can identify specific molecules and estimate their concentrations at different altitudes. For Neptune, the most important chemical targets are methane and its photochemical breakdown products, including acetylene, ethane, and diacetylene, whose concentrations at stratospheric altitudes should correlate with the level of photochemical activity driven by solar ultraviolet input. If those concentrations change between 2003 and 2020 in ways that altered the stratosphere's thermal properties, that change should be detectable in Webb spectra compared to estimates of historical concentrations derived from earlier instruments. Hydrogen cyanide is another important target. It forms in Neptune's atmosphere through reactions involving nitrogen and hydrocarbon fragments produced by ultraviolet photochemistry. Its concentration at different altitudes reflects the history of photochemical activity in the upper atmosphere. Tracking hydrogen cyanide abundance with Webb over the coming years would provide a direct chemical record of how the solar cycle has been driving photochemistry in Neptune's stratosphere. Acetylene, ethylene, and other hydrocarbon species produced by methane breakdown all have specific infrared absorption signatures that Webb can detect. Building a comprehensive chemical map of Neptune's stratosphere at different latitudes, including the warm South Pole and the cooler surrounding regions, would give scientists the data needed to test specific mechanisms for the cooling, the polar spike, and their potential connection to each other. the orthohydrogen and parahydrogen ratio, the balance between the two spin states of molecular hydrogen, is another candidate for Webb measurement. Different ratios produce slightly different infrared emission patterns that Webb's precision should be capable of distinguishing. If the cooling drove a shift in the orthohydrogen to parahydrogen ratio that in turn drove further cooling through a feedback mechanism, tracking that ratio across latitudes and over time would reveal whether the feedback is operating and at what magnitude. These are not distant future measurements. They are current science goals for Webb's Neptune observing program. The spectra are being collected. The analysis pipelines are being developed. The comparisons to historical estimates from earlier instruments are being prepared. The answers may come within a few years. They may come within a decade, but they are coming from data that is being accumulated right now. When they come, they will not resolve everything. Neptune's atmospheric system involves enough coupled processes that understanding the mechanism behind the 2003 to 2020 changes will open new questions about how those mechanisms interact over longer timescales, how they behave during different phases of Neptune's seasonal cycle, and how they compare to what is happening in Uranus's atmosphere on the other side of the solar system. Uranus and Neptune are not identical. Their atmospheres differ in ways that have been partially characterized but not fully explained. Uranus, despite being closer to the Sun than Neptune, is actually colder in its stratosphere, one of the ongoing mysteries in ice giant science. Whether the photochemical cloud seeding mechanism that Neptune has revealed operates on Uranus in the same way, with the same solar cycle correlation and the same 2-year lag, is an open question. Answering it requires the same kind of long-term systematic monitoring for Uranus that the 2003 to 2020 campaign built for Neptune. Some of that monitoring exists. A complete comparative picture does not. The ice giant decadal priority mission, if it moves forward and reaches one or both planets within the lifetimes of the scientists who are advocating for it today, will transform this entire field. An orbital spacecraft can measure what a telescope observing from billions of miles away can only approximate. Atmospheric composition at multiple altitudes, not just the upper stratosphere visible to remote sensing. Wind speeds tracked by following individual features continuously rather than comparing snapshots separated by months. Temperature profiles from the cloud tops deep into the troposphere, not just the stratospheric altitudes accessible to infrared remote sensing. Magnetic field structure mapped in 3 dimensions as the spacecraft orbits. Moon observations conducted from close range over extended periods rather than during a single flyby lasting hours. The science that would come from even one of those capabilities, sustained over years of orbital observations, would dwarf everything accumulated in the decades since Voyager 2 flew past. Neptune has been patient for 4.5 billion years. It will wait for the orbiter. In the meantime, the data keeps accumulating. The models keep improving. The questions keep getting sharper. And somewhere in the infrared spectra that Webb is collecting right now, in the thermal maps that ground-based observatories continue to build one observing season at a time, in the photographic record that future surveys will extend beyond the 26 years already assembled, Neptune continues to reveal what it is. Slowly, quietly, in wavelengths of light that no human eye can see. Across 2.8 billion miles of empty space between a cold blue planet and the instruments that are finally good enough to read it.